Trying to predict what our sun is going to do next, that is one of the biggest challenges in all of space science. And it's a huge deal because things like solar flares and storms can have a massive impact right here on Earth. So forecasting the sun's roughly 11-year activity cycle is a top priority. Let's dive into the incredible story of how scientists are finally cracking that code.
So the big question is, how in the world do you build a crystal ball for a star that's 93 million miles away? How can we reliably predict its behavior, especially the strength of its next cycle, years and years in advance? I mean, it's a puzzle that has stumped some of the smartest people on the planet for decades.
So check this out. For decades, the answer has been hiding right here in this data, in plain sight. This chart tracks 40 years of solar activity. You see the lines going up and down, showing the peaks and valleys of that 11-year cycle. But what I want you to do is focus on that solid black line. That line measures the magnetic field strength at the sun's poles. And as it turns out, it's the single best clue we have. The strength of that polar field at the end of one cycle literally tells us how strong the next one is going to be.
Okay, so to really get a handle on this polar field, scientists don't just, stare at the sun. They build a virtual one inside a computer. And the tool they use to do it, it is absolutely incredible. They're called surface flux transport models, or SFT models for short. The best way to think about them is as digital twins of the sun's surface. These are these incredibly complex simulations that track how magnetic fields pop up, drift across the solar surface, and then eventually gather at the poles.
Probably the best way to wrap your head around this is to think of it like a really, really complex weather forecast. You know how meteorologists use models to predict how temperature and pressure are going to move around to forecast a storm? Well, solar physicists use these SFT models to predict how magnetic flux is going to move to forecast a solar cycle. It's kind of the same idea, just on a stellar scale.
And just like a good recipe, an SFT model has these key ingredients you have to get exactly right. There are 3 main dials they have to tune. First, there's the speed of the flows moving from the equator up to the poles. Second, you have the rate of magnetic spread. They call it diffusion. And third, there's this kind of mysterious field decay time, which is basically how quickly the magnetic field just disappears.
Right, but here's the massive problem. What are the perfect settings for those dials? I mean, what are the right amounts? If you set them wrong, your virtual sun will behave nothing like the real one. For years, finding the right combination of these 3 things has been the central, nagging mystery of solar cycle prediction.
So, how do you crack a puzzle like that? Well, you do it the hard way. You run thousands upon thousands upon thousands of simulations, each one with a slightly different recipe, and then you check every single one of them against reality.
And we're back to our trusty chart of real solar observations. You got to think of this as the answer key. Any virtual model that scientists build has to be graded against this. It's not enough for it to just look plausible. A successful simulation has to perfectly recreate these exact patterns, especially how and when those polar fields flip and rebuild over 40 years of real history.
And out of everything, the most important test, the one thing that a model has to get right, it all comes down to timing. The sun's entire magnetic field, it's called its global dipole. It flips about halfway through each cycle. And we know from observations, this reversal happens very precisely, about 3.4 years after the cycle's minimum. A model has to nail this timing. If it's off, it's a failure. It's back to the drawing board.
So after running thousands of these simulations, a really fascinating pattern started to pop up. And it wasn't from the successful models, it was from the failures. And this is where the story gets really good.
Okay, so look at the left. You see a successful simulation. The green line is the solar cycle, and just watch how that orange line, that's the polar field, it flips right around the peak of the cycle, just like it does in real life. Now look at the failed model on the right. See that? The orange line doesn't flip until way later, long after the cycle's peak, and this exact same failure kept happening over and over and over again.
And this, right here, is the aha moment taken straight from the research paper. The scientists realized that every single time they ran the model without a significant field decay term, that's our 3rd ingredient, remember? The simulation failed in the exact same way. The magnetic poles always flipped too late.
So what does that all mean? It means that this mysterious 3rd ingredient, this field decay time, it wasn't just some minor tweak you could ignore. It was the missing key, the crucial missing piece that made the entire puzzle work. It had to be there. And it had to be in the right range. So what's the payoff here? It means that scientists finally found the recipe.
They found what you might call the Goldilocks zone for creating a virtual sun that behaves just like the real thing.
So what is that magic number? What's the just right setting for this field decay? Turns out, it's not infinitely long, like some of the older models just assumed. The research found it has to be somewhere in the range of 5 to 10 years. Not too fast, not too slow, just right.
In this beautiful map, this is the reward for all that painstaking work. It visualizes that Goldilocks zone. Any combination of flow speed and magnetic spread that falls within those brightly colored areas, when you combine it with that 5 to 10 year decay time, produces a successful model. The dotted areas, those are all the failed recipes. We now have a blueprint for how to do accurate solar forecasting.
Okay, that's all great for the scientists, but why should you care about any of this? Well, it matters a lot actually, because a reliable recipe for solar cycles means we get better, more accurate space weather forecasts. That helps us protect our crucial satellites, our GPS and communication systems, and even our power grids down here on Earth from the sun's most powerful eruptions. It's a fundamental leap forward in understanding our home star.
So, in the end, by treating this whole thing like a giant cosmic recipe and testing thousands of different variations, scientists didn't just stumble on an answer. They figured out the fundamental rules for building a virtual sun. They found the missing ingredient. It really makes you wonder, now that this code has been cracked, what other solar mysteries are we on the verge of solving next?